Hello. Today I would like to show you how to create a simple 3D Perlin noise generator for Godot 4.1. 3D noise textures like this are super useful for doing something like driving the density value for a given point in a volume. So to jump right in, we're going to start by making a 2D Perlin Noise Shader, and we will then build our 3D noise off of that. What is Perlin noise? Or even noise in general in this context? Sometimes when we are coding, we want to get a random number. Random numbers can be used to create random procedural effects like color gradients or even mesh displacement. However, in the context of shaders, we cannot just simply use a random number for each fragment, as this would have a sort of TV static effect on our mesh, depending on what we are using this random value for. So what we need instead is to have a coordinate space, whether it is 2, 3, or even 4 dimensions, where random values are generated on a divided grid, and the values between each random value are interpolated. This way, we still get the randomness we want, but with a nice smoothness in between, giving it a natural look. Perlin noise is one of the most widely known procedural noise algorithms, widely used in computer graphics applications. So we're going to start to build this 2D noise texture, and we're going to display this texture on a 2D plane here in Godot. So I'll create a mesh instance and select plane. Now I'll go here and create a new shader material. Let's create a new shader and we'll call it 2D Perlin noise. Okay, and now I'll open up the shader. And I'm going to set the render mode to unshaded so we can ignore lighting data and show our texture in full color. Let's create a color gradient across the entire UV of the plane. I will pass the vertex local space position for each vertex to the built-in color variable of the vertex function, which will interpolate the values across the local X and Z axes of the plane. If that's confusing, just know that color values are created from combining 4 separate float values that correspond to the colors red, green, and blue, and what we call alpha, which represents the opacity or transparency of the object. But if we do not care about opacity, we can just think of the first 3, R, G, and B. Each of these values will be a float between 0 and 1, and all the colors you see on your screen are a combination of these. In the context of 3D graphics, you can think of this combined RGB value as a 3-dimensional vector. This concept is most apparent in normal maps, where differences in the surface's normals correspond to variations in color on the normal map. You may also note that to help everyone's brains with this, most 3D softwares use each of those colors to represent their corresponding axes. X is always red, Y green, Z blue. So we can see this as well on this color gradient we have created. All of the colors converge into black at the center, where the position vectors for each fragment are approaching 0. Then you can see it is red where the position reaches 1 on the X-axis and blue on the Z-axis. So for the sake of visualization, I want to make it so that this bottom corner vertex sorta acts as the origin for our color gradient. So instead, I am going to pass the UV coordinates to color. And you can see now that at this corner, the values are 0, and here they move up to 1 on both axes. So the reason I want to show the increasing values like this is so we can visualize the grid with which we will generate our smoothly interpolated noise. So to create the grid, we have to create 2 different variables, grid index and grid fract. For grid index, we will use the floor operation on the UV coordinates. And for grid fract, we will use the fract operation. Floor will take the values and return the integer component of each value, and fract, short for fraction, I think, will return the decimal component of the value. So for a value of, let's say, 1.67, floor will return the integer 1, and fract will return only 0.67. So if we pass grid index into albedo, it turns the whole thing black because every coordinate value on here is below 1. we can see that passing gridfract gives us the same as what we had before. But now if I create a variable for the UV and scale the UV up, now we have this grid we want starting to show up. I'll set this to, let's say, 5 for now. So now we have a two-dimensional grid where the origin of the cell is at the bottom left point. The way we're going to create our Perlin noise from this grid is first by assigning a random vector, or gradient in this context, to each of the cell's corners. This vector will have a random float assigned to its x and y axes between -1 and 1, or 0 and 1, depending on what you want your noise to look like. So now that we have all our random vectors, when our fragment shader goes through each individual fragment of this UV grid, it will take the coordinates of that point in whatever cell it's in, and it will find the distance between that point and all 4 of the cell's corners. Then you are going to get the dot product between the random gradient vector for each corner and that distance value for each corner. And lastly, to get the noise value for that fragment, you're going to use bilinear interpolation, which in practice would be linearly interpolating the bottom left value with the bottom right, then top left with top right, and then linearly interpolating the bottom value with the top value, which is essentially bilinear interpolation, 2 separate axes. And to make sure that the transitions between the values on this noise texture are smooth, you can use a smooth step function in the interpolation. So now that we know how the Perlin noise algorithm works, we can start writing the rest of it in our Godot shader. So first things first, we are going to want to create a function called random2d, which will return a random vector 2 with values between -1 and 1. In GDScript, there are built-in number generator functions, but since this shader code is run on our GPU at fast speeds, it is simplest just to write our own random number generator function for this. So due to the deterministic nature of computer processors, these numbers are pseudo-random, as the true randomness can never be achieved. But this function I found online somewhere seems to do the trick. Looks a bit strange, so let's see what's going on here. This function takes the vector2 coordinates that the random vector will be created off of, so we are going to be using each of the cell corners later in the noise algorithm. This part here is taking the dot product of the UV coordinates and some arbitrary constant values. The function I pulled somewhere off the internet used these values. I haven't experimented too much with these values because some people tweak these values to find the best looking noise, and the values I found online here worked fine for me, so feel free to copy these numbers exactly or use your own. What this does is sort of disorient the UV coordinate system to help it look more natural and random. And then down here we use this fract sign of those UV coordinates, which is a quick way of breaking up the sine wave into pseudo random values multiplied by this big number here to create an even more random and jagged distribution of values similar to this image. And this part with the -1 plus 2 keeps the random value within -1 and 1 of the UV coordinate the random vector is based on. So anytime we pass a UV coordinate into this function, we will get out a random vector that is within -1 and 1 of that coordinate. Alright, so going down here, we have our grid indices and our actual fractional grid values. So now we're going to want to grab the 4 corners of the cell in the grid for this fragment. All we do is take the grid index. Bottom left will be at grid index plus 0 and 0. Bottom right will be at grid index plus 1 and 0. Top left 0 and 1. Top right 1 and 1. Here's a little visual of it if that helps. Alright, next step is we're going to create our random gradient vector for each corner. Alright, now once we have those, we're going to want to get the distance from the current fragment in the fragment shader to each of the 4 corners. We will do that with gridfract for the value of the current fragment minus the cell corner coordinate. But notice we do not use grid index to get these corners because our gridfract variable will always be within 0 and 1. Nice. So now that we have those, we have to find the dot product of the random vector for each corner and the distance vector for that corner. So now that we've written all this in the fragment function, I'd rather create a noise 2D function for all these calculations like this. So now that we got the dot products, we are going to want to linearly interpolate these values to get a single float value representing the noise value at the given fragment. We do this with the mix function, and we do bottom left with bottom right. And we will use grid fract x-axis as the factor. And then top left, top right, again with grid fract x-axis. Then we will mix the bottom with the top with grid fract y as the factor. Now we'll use the noise value for the UV coordinate inside a vector 3 to drive albedo. And look at that, we're getting close. Doesn't look much like the traditional Perlin noise. That is because our noise values are between -1 and 1. If you want it to be between 0 and 1 after this, you can just add 0.5 to the final value of the noise function, like this. We can increase the scale with this grid scale slider. You can see that there are still some jarring transitions between the cells, making the cell pattern still slightly visible. To fix that, all we have to do is use a smooth step function. Set the floor to 0.0, top to 1.0, and the value to smooth out will be grid fract. Then we just go down to the interpolation and change grid fract as the factors to this new blur variable. And there we go, working 2D Perlin noise. This just needs the object's UV coordinates to display the texture. So now we're going to create a 3D noise function based on this one. I'm going to create another shader called 3D Perlin Noise. I'm just going to copy and paste the 2D noise shader into this one so I can build on it. I'll rename these functions. Since this is going to be 3D noise, we will display it on a 3D cube. So let's pass the UV coordinates of this box to albedo. You can see from this how the box is unwrapped like this. This shows you how objects' UV coordinates are used to project 2D textures onto 3D objects. But how would we display a 3D noise texture on this 3D object? Instead of two-dimensional UV coordinates, we need the actual 3D coordinates of each fragment in local space to be the coordinate space for the 3D texture. We can visualize this by, like we did with the 2D texture, passing the vertex position to color RGB and passing that to albedo. It looks like this because the vector of 0.0x, 0.0y, and 0.0z lies exactly at the origin of the object in the middle. Similar to before, we can just add 0.5 to the vertex position, which will shift the vertex coordinates by 0.5 on all axes. Now you can see that this bottom front left vertex has a value of 0, so it is black, and the opposite vertex is white because all the values approach 1. So you can see how this will act as our 2D texture space. To visualize the cells in 3D, I can multiply the UVW space by the grid scale value just like before, and display it with this grid fract variable. Now if we slide the grid scale slider, we can see the cells. So the 3D Perlin noise works exactly the same way as 2D, but the random value for this cell is calculated with all 8 corners of a 3-dimensional cube, rather than 4 of a plane. So now let's go through and modify this 2D noise function. First, we are now going to take a vector 3 called UVW as a parameter, rather than UV. We're going to create 4 more corner points for the cube, and they will be front and back. I'll change these corner coordinates to vector 3 as well and add the z values. I'll do the same and add the random gradients to these new 3D coordinates. And actually, I forgot to fix our random number generator, because now we want it to generate a random vector 3 instead of a vector 2. Basically, we are going to have to copy the x and y axes of this vector 2 in the random function and make a z axis with new arbitrary constant values. I'll change everything else to vector 3 and make it take UVW as a parameter. Alright, now we can go down and create the distance vectors for each of the corners as well. And the same for the dot products. Alright, so before we interpolated left to right bottom, left to right top, and then top to bottom. But now we need to interpolate a third time for front to back. So now we got some trilinear interpolation. Let's see how it looks by putting the noise texture into albedo as a vector 3. And then just add 0.5 to the final output of the noise function to keep the values between 0 and 1. Alright, so there you have your 3D Perlin noise algorithm. You can perform operations on the UVW value at the beginning of the noise function to transform, rotate, scale, or even distort the 3D noise. You can even get a 2D slice of the noise texture by setting one of the axes of the UVW position passed to the noise function to 0. So, in the next video, we're going to be using this 3D noise texture to drive the internal density of a signed distance sphere using ray marching. It's going to be very fun to create, so I hope to see you in the next video. Thanks!